Hello. Today we will start the second part of the course, the study of thermodynamics. And we're going to start with a discussion on temperature and kinetic theory of matter. Well, anybody tell me what is the difference between temperature and heat? Very often we use these terms, heat and temperature. Well, what is the difference? Heat is a form of energy, and when heat is supplied to an object, it increases the internal energy of the object. Now, what is the meaning of internal energy? If you look at an object, the object is made up of tiny particles called molecules. And these molecules are bound together, and that boundness causes potential energy, and they move about producing kinetic energy. So basically the internal energy is made up of potential and kinetic energies. The internal energy of an object is made up of the kinetic and potential energies of atoms and molecules. Atoms and molecules have kinetic energy because of their vibrational, rotational and translational motion. So molecules may be vibrating, they can rotate, and translational motion is motion from one place to another. Potential energy of atoms and molecules are associated with their relative states or position. Now, potential energy of a system is greater when the objects are farther apart. Now, you know from our discussion on potential energy from Physics 1, if an object like this is lying on the ground, we would say the potential energy is zero. Now, if I lift it up, I do work, the potential energy increases. So, we say the potential energy of the Earth object system increases when the distance between them increases. Alright, now if you look at this, here I have broken this object into several pieces by sort of banging on it. Now that means its potential energy has increased. The work I did to break this open, that energy has been stored as potential energy of the fragments. The potential energy increases when they move apart. Now, the same phenomenon happens when you move molecules away from each other. In order to if the molecules are bound together, if you want to separate them and move them away, you've got to give energy. And that energy is a measure of the potential energy. So, internal energy, let's now talk about temperature. When heat energy is supplied to an object, its temperature rises. So, let's investigate what is the relation between heat and temperature. The rise in temperature is purely due to the increase in translational kinetic energy of the molecules. You see, the increase in temperature has nothing to do with the increase in potential energy. The increase in kinetic energy is due to the increase in the translational kinetic energy of the molecules. Now, let's have a look at the relation between temperature and translational kinetic energy. Now, if you look at the motion of molecules in here, most of our discussion is going to be geared towards gases. So here you have a large number of molecules and they are in a state of random motion. You see, this is at lower temperature. When the temperature increases, their translational kinetic energy will increase. Let's see what difference will there be at a little higher temperature. Now, this is at a higher temperature. The molecules are definitely moving faster. So, as temperature increases, the molecules will move faster. In other words, the temperature is a measure of the translational kinetic energy of the molecules. Now, look at this illustration. I have two beakers containing water. Now, this beaker contains a large amount of water and the small beaker contains a small amount of water. I supply heat to both of them at the same rate. Now tell me, which of them will have greater increase in temperature? Well, obviously, greater increase in temperature will be in the case of the small beaker. Why? Because the same amount of heat supplied to both is shared among less number of molecules in the small beaker than in the big beaker. That means the energy received per molecule will be greater here than here. And so, when you talk about temperature, it is good to understand temperature as being proportional to the average kinetic energy of the molecules. It is not a measure of the total kinetic energy. You see, the total kinetic energy of the molecules in the big one and the small one are the same. But the average kinetic energy of the molecules in the small beaker is greater than the average kinetic energy of the molecules in the big one. Therefore, the temperature in the small beaker is higher. Now, the larger quantity will have a smaller increase in temperature, while the smaller quantity will be a higher increase in temperature, because the average energy per molecule, is greater here. So how do we define temperature? Temperature of an object is proportional to the average kinetic energy of its molecules. It is a measure of the average kinetic energy per molecule. If the temperature is greater, means each molecule will have a much higher kinetic energy than when the temperature is lower. Now look at this illustration. The energy of an object, the internal energy of an object, is made up of potential energy and kinetic energy. Now I have two situations here. Look at this object. This is the amount of potential energy and this is the amount of kinetic energy. And coming over there, this is the amount of potential energy and this is the amount of kinetic energy. What can you say about the temperature of these two objects? You can see the average kinetic energy is the same in both cases. That means the temperature of both those substances are the same, because the temperature depends only on the average translational kinetic energy. The potential energies are different. The total internal energy also is different. But the temperatures are the same here because the kinetic energies are the same. Alright, let's move on. Let's talk about measuring temperature. Well, we all know we measure temperature using a thermometer. Is that right? In order to measure temperature, we make use of properties of materials when heat is supplied to an object. Now tell me some properties of materials that will change when you supply heat. Well, when heat is supplied, objects will expand. Is that right? So that property can be used to measure temperature. For example, most substances expand when heated, and therefore increase in volume is very nearly proportional to the change in temperature, and as a result, the increase in volume of a substance can be used to measure temperature. In fact, most of our thermometers that we use this property. when heat is supplied to a substance, its volume increases, and the increase in volume is very nearly proportional to the increase in temperature. Well, mercury or alcohol in glass is a very good way of constructing a thermometer. So we normally use two types of thermometers in the lab. One is the mercury in glass thermometer, and the other is alcohol in glass. Now here I have both. This is mercury in glass, this is alcohol in glass. You can see alcohol can be colored, so it is much more easily visible. And most of the thermometers we use these days in the lab especially is alcohol in glass thermometers. The reason why we don't use a lot of mercury thermometers is that if you break a thermometer, mercury gets spilled and it is a poisonous substance. So a thermometer like this, when you keep this inside, say, a substance where you want to measure the temperature, the volume of the alcohol will either increase if the temperature is higher or decrease if the temperature is lower, and you can calibrate the thermometer to read the temperature. We will look at that as we go on. Let's now talk about temperature scales. There are two main scales of temperature used in measuring temperature. What are they? One scale is called the Celsius scale, and it uses an arbitrary temperature, namely the temperature at which ice melts at the atmospheric pressure as it's 0. So on the Celsius scale, 0 of the Celsius scale is the temperature at which ice melts at atmospheric pressure. So 0 degrees Celsius is called the ice point, the temperature at which ice will melt at atmospheric pressure. The other scale is called the Kelvin scale, uses temperature at which the molecular energy is 0. It's also called the absolute scale of temperature. So the 0 of the Kelvin scale is the temperature at which the molecular vibrations will be absolutely 0. It's a very difficult state to reach, and it is a very low temperature, and you've got to go down to almost 273, negative 273 degrees Celsius, and that is 0 Kelvin. So 0 Kelvin is the temperature at which molecular energies are absolutely 0. Alright, in the Celsius scale, the temperature is measured in a unit called the degrees Celsius. So in a Celsius scale, we have temperature measured in degrees Celsius, while in Kelvin scale, we measure it in a unit called Kelvin. We don't use degrees when we measure it in Kelvin. We say 25 Kelvin, 250 Kelvin, and so on. Whereas in Celsius, we say 10 degrees Celsius, 15 degrees Celsius, and so on. Now, when you measure temperature in degrees Celsius, we use lowercase t to represent that. And when you measure temperature in Kelvin, we will use uppercase temperature to represent that. Alright? So lowercase temperature to represent temperature in degrees Celsius, uppercase T to represent temperature in Kelvin. So what is the relation between uppercase T and lowercase t? Degrees Celsius and Kelvin. T Kelvin is T degrees Celsius plus 273.15. What that means is the 0 Kelvin is negative 273.15. You got to go up to 273.5 to reach 0 degrees Celsius. Alright, So this is 273.15 Kelvin. 0 degrees Celsius is the same as 273.15 Kelvin. And what is the upper point for the degree Celsius? The temperature corresponding to boiling water is what is called 100 degrees Celsius. And what is the corresponding temperature in Kelvin? That is 373.15 Kelvin. So this gives us a picture of the relation between temperature measured in degrees Celsius and temperature measured in Kelvin. Alright, let's now look at mercury in glass thermometer. A quick look at the thermometer. A mercury thermometer is used in the laboratory, are marked in degrees Celsius, and use the property of expansion of mercury with temperature. We talked about that. Here is a mercury in glass thermometer. The length of mercury column in the stem of the thermometer varies linearly with the temperature of mercury in the tube. Now, the discussion I'm having with mercury is equally valid for alcohol. Alright? So, you can substitute alcohol with mercury at any time in this discussion. So, 2 fixed points are marked on the stem. Once you get the thermometer made, you need to make 2 fixed points on the stem. What are they? The lower fixed point corresponds to the temperature of melting ice. So what you do is, you put this thermometer in melting ice, and when the level of the mercury becomes steady, you make a mark on the thermometer, and that will be called the lower fixed point, which is 0 degrees Celsius. And then cover this with boiling water at atmospheric pressure. The level of mercury will rise, and when it becomes steady, make a mark and call it the upper fixed point, which will be 100 degrees Celsius. And then all you need to do is, the interval between the 2 fixed points are divided into 100 equal parts. Alright. Now watch this carefully. If L0 is the length of the mercury column at 0 degrees Celsius, so if this is L0, the length at 0 degrees Celsius, and L100, its length at 100 degrees Celsius. L100 is this length at 100 degrees Celsius. Now, and suppose L sub t is the length at t degrees Celsius. You see, we have now got the lower fixed point and the upper fixed point of the thermometer. We now put this thermometer in a bath where you want to measure its temperature. And if L sub t is the length of the mercury column at that time, so this is L sub t. Using these 3 lengths, these 3 values of the lengths of mercury column, we can now calculate the temperature T like this. Now take a note of this equation. T degrees Celsius equal to LT minus L0 divided by L100 minus L0 multiplied by 100. So once you know the lengths of these, you can calculate the temperature. Alright? Let's do a simple problem. The length of a column of mercury in a thermometer is 4 centimeters when it is immersed in ice water. So this is L0. And 24 centimeters when it is immersed in boiling water. This is L100. What is the length of the mercury column at 22 degrees Celsius? This is T degrees Celsius. We need to find the length of the mercury column at that temperature. All right, let's do that first. What do we have? There is the thermometer. L0 is 4 centimeter. L100 is 24 centimeter. The temperature is 22 degrees Celsius. There we go. L0 is 4 centimeter. L100 is 24 centimeter. And the temperature is 22 degrees Celsius. We want to find the length L sub t at that temperature. What do? Go to our equation. T degrees Celsius is LT minus L0 over L100 minus L0 multiplied by 100. We have T degrees, we have L0, we have L100. Solve for T. I'm sure you can do that. So put all the given values and now solve for the value. Now solving for V, I'm going to leave it for you to solve it. I'm sure you know how to solve it. Now solve with the denominator, then cross multiply. Is that right? Well, try that on your own. Solving gives you L sub t equal to 8.4 centimeter. Alright, let's see what the B part is. If the length of the mercury column is 25.4 centimeter when immersed in a chemical solution. So this time we have L sub t. We want to find the temperature of the solution. Well, we go back to our equation. Is that right? T degrees Celsius is this. Now, we know L sub t, which is 25.4, and we know L0, we know L100, and so simply put all those values. That gives you T degrees Celsius is 107 degrees Celsius. Okay, let's now look at another type of thermometer called constant volume gas thermometer. Now, what does that mean? Constant volume gas thermometer. Now, what it suggests is that this thermometer will keep its volume a constant all the time. Now, if the volume is going to be a constant, what is going to now change? What change are we going to measure the temperature? Well, it's going to be the pressure. So we keep a certain amount of gas at a constant volume, and then the increase in pressure will be proportional to the temperature. So the increase in pressure then can be used to measure temperature. So the pressure of a fixed mass of gas enclosed at a constant volume changes linearly with temperature. That means the change in pressure at constant volume is a good measure of the temperature. I have a diagram of that arrangement here. Here I have a bulb which contains a gas. In this case, we have the gas enclosed in here. B1 is the bulb that contains the gas. Now it is connected to another bulb, B2, and that B2 is connected by a rubber tube to a third glass tube. Now this glass tube can be raised or lowered, and you can see it contains mercury. Mercury is contained in here, and by raising or lowering the tube on the right, you can change the level of mercury in the closed tube. You see, this is the closed tube. That's the open tube. Now, whenever we take a measurement, always bring the mercury level to this, against this arrow, to make sure that the volume of gas inside the bulb remains a constant. And if you remember, we talked about how to measure pressure. You see, when the levels of mercury are the same, for example, if the level of mercury in the open tube is also here, then the pressure of gas inside here is atmospheric pressure. Tell me, the level in the open tube is here, the level in the closed tube is here, therefore is the pressure of gas inside, is it greater or less than the atmospheric pressure? It is much greater, because this pressure due to this gas has pushed down the mercury column much lower than it is that is open to the atmosphere. So what all you need to do is measure the difference between the levels and add it to the atmospheric pressure. What is the normal atmospheric pressure? 76 centimeters of mercury. And measure H in centimeters and add it to that. It will give you the pressure of the gas inside. And now, when you enclose this inside a bath, water or anything else where you want to measure the temperature, and you heat it slowly, what will happen? You can see the volume of gas will change. But whenever you want to measure the temperature of that bath, you need to adjust this reservoir, bring the mercury level to this fixed mark, making sure that the volume remains a constant. Then measure the difference in the pressure and add it to the atmospheric pressure to get the pressure of the gas inside. And the measure of the pressure can then be calibrated to read the temperature. So the pressure of the gas enclosed in the tube can be measured by keeping its volume always a constant. Now, if P0 is the pressure of the gas when the bulb of the thermometer is covered in melting ice, you see, cover the bulb of the thermometer in melting ice and measure the pressure of the gas, and that would be P0. In the same way, cover the bulb of the thermometer in steam at atmospheric pressure. Again, change the level of the mercury to bring it to the fixed mark and measure the pressure. That will be P100. And at any given temperature, if the pressure is PT, then you have a similar relationship in here. T degrees Celsius equal to PT minus P0 over P100 minus P0 multiplied by 100. It's a similar relation that we saw earlier. That means if you P0 and P100 can be easily measured, and PT can be measured anytime you want to measure the temperature of a bath. Cover the bulb inside the bath and measure PT, and therefore the temperature can be calculated using that relation. Let's do a simple problem. The pressure recorded by a constant volume gas thermometer is 0.4 atmosphere at the ice point and 0.546 atmosphere at the steam point. When the pressure is 0.1 atmosphere, what is the temperature? Well, what do we have? P0 is 0.4 atmosphere. P100 is, what's our P100? P100 is 0.546 atmosphere. And PT, the pressure at a particular temperature, the temperature we want to measure. The pressure at a temperature that we want to measure is 0.1 atmosphere, and therefore what is the temperature? T degrees Celsius is PT minus P0 over P100 minus P0 multiplied by 100. And all those values you know, therefore that temperature is negative 205.5 degrees. You see, what is the advantage of a thermometer like this? A constant volume thermometer. Can you use a mercury thermometer to read a low temperature like this? No. Even a very high temperature, like 200 degrees Celsius, you cannot use a mercury thermometer. The range of a mercury thermometer is very limited. So, If you use a constant volume thermometer, you can measure temperatures very low or very high without trouble. That's the advantage. Alright, let's do the B part. What is the pressure at 444.6 degrees Celsius? This time you have the temperature, you need to measure the corresponding pressure. Alright, we again go back. We know P0, we know P100, and we know the temperature. We got to find the pressure at that temperature. We need to solve for PT. So we use all the given values and solve for PT. Again, I'm going to ask you to do that on your own. I think I have worked that out for you. Simplify the denominator, that gives me this. And now cross multiply, this multiplied by that will be 0.649 is PT minus 0.4. Therefore, PT equal to 1.049 atmosphere. A good way to use a constant volume thermometer. Okay, we will now look at another way we can measure temperature rather than depending on the ice point and the steam point. You see, ice point and steam point are not very easily reproducible fixed points. You know why? Because they depend so much on the external pressure. So, we are now going to look at what is called the triple point temperature. The ice point and steam point are not very easily reproducible all the time. Now, a reference point which is more precisely reproducible than the ice point and the steam point is the triple point of water. What is the triple point of water? You see, there is a particular temperature at which water will exist as solid, liquid and vapor at the same time. And that temperature is called the triple point of water. You think that's possible? Can solid and gas exist at the same time? Well, if you want to know, just open your freezer compartment and see how solid ice and vaporized water can exist at the same time. Well, the triple point is the unique temperature and pressure at which water, water vapor and ice will coexist in equilibrium. Now the ideal gas temperature is defined in such a way that the temperature of the triple point is 273.16 Kelvin. The temperature of the triple point is 273.16 Kelvin. Now, the temperature of any other state can then be proportional to the pressure in the constant volume thermometer. Now, we're going to use the same constant volume thermometer there, and let's look at the relation connecting the triple point pressure and the temperature we want to measure. If T is the Kelvin temperature when the measured pressure is P. So, you want to measure the temperature T Kelvin, you cover the bulb of the thermometer with that particular bath and measure the pressure P. We have now a relation connecting the temperature of that bath, the pressure corresponding to that temperature, and the triple point pressure. And this is the relation. T equal to 273.16. What is this? This is the triple point temperature divided by P3. What is P3? The triple point pressure. So, triple point temperature divided by the triple point pressure multiplied by the pressure at that temperature. So, take a note of this equation. T equal to temperature in Kelvin equal to 273.16 over P3 multiplied by the measured pressure at that temperature. Now, P3 is the pressure when the thermometer is immersed in a water ice vapor bath. That's right, and that's the triple point pressure. Alright, let's use that to solve a problem. A constant volume gas thermometer has a pressure of 30 torr. You remember the unit of pressure we taught? Torr. The torr is a millimeter of mercury. When it reads a temperature of 373 Kelvin, so a pressure of 30 torr corresponds to a temperature of 373 Kelvin. What is the triple point pressure P3? Alright, let's do that. We know the pressure, we know the temperature, we know the corresponding pressure. We need to find the triple point pressure. Well, once you know that equation, we have no problem there. Pressure P is 30 torr. The corresponding temperature is 373 Kelvin. T equal to 273.16 over P3 multiplied by P. We have P, we have T, we can find P3. So 373 equal to 273.16 over P3 times 30. Or P3 equal to, is that right? I can simply swap positions. P3 equal to 273.16 over 373 times 30. That is 21.97 torr. And this is the triple point pressure. The pressure of the gas inside the constant volume thermometer when the bulb of the thermometer is covered in water ice steam bath. Alright. Next one. What temperature corresponds to a pressure of 0.175 torr? Well, we can now calculate the pressure, we can now calculate the temperature corresponding to this pressure because we have calculated P3. Alright? What is P3? The calculated P3 is 21.97 torr. And the measured pressure is 0.175 torr, and we need to calculate the corresponding temperature. Well, put the value of P3 and simplify, and that will be 2.18 Kelvin. Okay, let's move on. Let's now talk about gas laws. You see, when you want to study the behavior of gases, there are three important states for a gas. You have the pressure, you have the volume, and you have the temperature. Now, it is impossible to study the variation of pressure with volume without keeping the temperature a constant. In the same way, if you want to study the variation of pressure with temperature, you need to keep the volume a constant. That's what we did in constructing the thermometer, constant volume thermometer. In the same way, if you want to study the relationship between volume and temperature, you need to keep the pressure a constant. So, therefore, we have three important studies about a gas. What are the three important studies? The three important studies are, we will study the variation of pressure and volume when temperature is kept a constant. So we will study, we have a gas enclosed inside here. We will study the relationship between pressure and volume when the temperature increases or decreases. And that relationship is Boyle's law. Then we will study the relation between pressure and temperature when volume is kept a constant. And then we will study the relation between volume and temperature when pressure is kept a constant. So these are the three studies we will make. All right. The state of a gas can be described by its pressure P, volume V, and temperature T. In order to study the relation between pressure and volume of a fixed mass of gas, we have to keep its temperature a constant. Now, such a relation is given by Boyle's law. So what do? You keep a gas at the same temperature. Whenever you want to measure the pressure and volume, you keep the gas at the same temperature. And then study its pressure and volume. The pressure of a fixed mass of gas is inversely proportional to its volume when temperature remains a constant. The studies have been done by many people. So we are not going to do a study, we're going to accept their result. And the result is this, which is the statement of Boyle's law. So what is the statement of Boyle's law? It says the pressure of a fixed mass of gas is inversely proportional to its volume when temperature remains a constant. What does that mean? When temperature remains a constant, if you increase the pressure, the volume will decrease. That makes sense, is that right? In the same way, by keeping the temperature a constant, if you increase the volume, the pressure will decrease. Well, this law can be written as, how do you write that law? Well, P times V is a constant when T is a constant. You see, pressure is inversely proportional to volume. We write it like this. P is proportional to it. Now you understand that. Inverse proportion, 1 over V, or pressure equal to a constant divided by V. Now, that is the same as pressure multiplied by volume remains a constant. So, P times V remains a constant. What does it mean? It means if you have P1 and V1 are the pressure and volume for a gas in state 1, and if you change that to P2, V2 without changing the temperature, then P1 multiplied by V1 will be equal to P2 multiplied by V2. That's the meaning of that. So, we have the statement of Boyle's law. The variation of pressure with volume of a gas at constant temperature is called an isothermal change. What's the meaning of isothermal? Isothermal means when temperature remains a constant. So any change that happens when the temperature remains a constant is called an isothermal change. Now, if you make a plot of pressure against volume, how will that plot look like? You can see, as volume increases, pressure will decrease. Is that right? And so, a plot of pressure versus volume will look like this. Pressure on the vertical axis, volume on the horizontal axis. Now, this plot is at a temperature T1. If you now do the experiment using the same amount of gas at a temperature, higher temperature T2, that will be the plot of pressure versus temperature, and still at a higher temperature. So these three curves represent plot of pressure against volume at three different temperatures, and each of these is called an isotherm. So the plot of pressure against volume at constant temperature is called an isotherm. Is that right? Okay, let's move on. Let's talk about pressure law now. Well, you should be able to define that for me now. Pressure law. What will that? a relation between pressure and temperature when volume remains a constant is given by the pressure law. Now, what does the pressure law say? We can enclose a gas at constant volume and then measure its pressure at different temperatures, and we can actually make a plot of pressure against temperature. Is that right? And we can arrive at a conclusion, and this is the conclusion. What does the conclusion say? The pressure of a fixed mass of gas is directly proportional to its Kelvin temperature. Well, note that carefully. The temperature this time is in Kelvin scale. The pressure of a fixed mass of gas is directly proportional to its Kelvin temperature when volume is a constant. Now, the pressure law can be represented. Now, can you help me represent that by an equation? Pressure is directly proportional to temperature. So, I will be able to write it like this. Pressure is directly proportional to Kelvin temperature, or pressure equal to a constant multiplied by the Kelvin temperature, which is the same as P divided by T will remain a constant. You see that? So, when volume remains a constant, pressure divided by the Kelvin temperature will be a constant. That means if P1 is the pressure at a temperature T1, and later on if the pressure changes to P2 when the temperature is T2, it means P1 divided by T1 will be equal to P2 divided by T2. That's the meaning there. So we have P over T is a constant when the volume V is a constant. And that's what the pressure law is. Now, a plot of pressure against temperature in Celsius scale. Now, we can actually do this experiment in the lab. We can take the bulb of the thermometer and cover it in ice, measure the temperature in degrees Celsius, and gradually heat the ice, and at intervals of 10 degrees you can keep measuring the pressure. So a plot of pressure against temperature we can plot as a result of that. So what did I say we do? We cover the bulb with melting ice and measure its temperature, measure its pressure, making sure that the volume is a constant. So I can make a table. Well, let me make a table there. Temperature in degrees Celsius and the pressure. So when temperature is 0, I can measure the pressure. Temperature is 10 degrees, I can measure the pressure. Temperature is 20 degrees, I measure the pressure. 30 degrees, I measure the pressure. And draw a graph of P against T in Celsius. Watch that, it is in degrees Celsius. So draw a graph of pressure against temperature in Celsius. This is the graph you get. And the most interesting characteristic of that is, if you extrapolate that graph and allow it to meet the temperature axis, it will meet the temperature axis at negative 273.15 degrees Celsius, which is 0 Kelvin. And that is the temperature at which a gas ceases to have any pressure. That is absolute zero of temperature. So tell me now, instead of knowing that this is 0 degree Kelvin, instead of drawing the graph of pressure against temperature in degrees Celsius, if I draw the graph of pressure against temperature in Kelvin, what will the graph look like? The only difference is that the origin of the graph will shift to this point at 0 Kelvin. Is that right? So a plot of pressure against temperature in Kelvin passes through the origin like this. And you know that when a straight line graph passes through the origin, it means the independent variable P is directly proportional to the, well, the dependent variable P is directly proportional to the independent variable T. P is proportional to T. That's what this graph tells you. And that's what the pressure law tells you. Alright, let's now talk about Charles' law. Well, now you know what Charles' law is going to be. This time, you're going to keep the pressure a constant. A relation between volume and temperature when pressure remains a constant is given by Charles' law. And what is the law? It says the volume of a fixed mass of gas is directly proportional to its Kelvin temperature when pressure is a constant. Well, we can write it like this. Like what? Volume is directly proportional to the Kelvin temperature. That means V over T is a constant when P is a constant. What does that mean? If V1 is the volume at a temperature T1, and after some time, if V2 is the volume at a temperature T2, then V1 over T1 will be equal to V2 over T2. That's the meaning. V over T will remain a constant as long as the pressure will remain a constant. Now, in a similar way, a plot of volume against temperature in degrees Celsius will look like this. Volume against temperature will be a graph like this, which will meet the temperature axis again at 0 Kelvin. So if you plot now the graph of volume against temperature in Kelvin, what will that graph be? It will pass through the origin, telling us that V is directly proportional to Kelvin temperature, and that is Charles' law. So we discussed 3 laws now. Can you recall those 3 laws? Boyle's law tells us that P times V remains a constant when the temperature is a constant. And you know, a change when the temperature remains a constant is called an isothermal change. Alright, what is the next law? Well, the pressure of a fixed mass of gas is directly proportional to the Kelvin temperature. P over T is a constant. And finally, Charles' law, V over T is a constant. Alright, let's now put all these 3 laws together and come up with what is called the ideal gas law. Most of you are familiar with this from chemistry. Well, these 3 laws together can be expressed in one statement. And what is that one statement? P times V equal to C times T, where that C is a constant. Does it make sense? Well, let's write down these 3 laws. We said P times V is a constant. P times V is a constant. Is that right? When T is a constant. P over T is a constant when V is a constant. And V over T is a constant when P is a constant. So we would put all these 3 together and say, therefore, PV over T is a constant. I'm going to call that constant C. So, combining all the 3 equations, we have PV over T is a constant. And I can write it like this, PV equal to a constant times T. That's what this is. PV equal to a constant times T. And that is a combination of all the three laws. Now here C is a constant and its value depends on the amount of gas. The value of that constant will depend on how much gas is in the sample. How many moles of gas? You know that the amount of substance is measured in a unit called mole. Okay, now C can be written as C equal to K times N, where N is the number of molecules in our gas. We have a sample of gas, a fixed quantity of gas, and N here is the number of molecules of that gas. And K is at another constant. You see, the number of molecules in a fixed amount of gas is a constant. So N is a constant and K is another constant. It's a very important constant in physics. It's called, K is a constant called Boltzmann constant. So N is the number of molecules of the gas and K is a constant called Boltzmann's constant. And therefore we can write PV equal to, in place of C, I write K times N. Tell me, what is K? K is Boltzmann constant. I will give you the value of K in a minute. And N is the number of molecules in the gas. Don't forget that. So, the value of K is determined as, it's been measured, and this is the value of K. K equal to 1.381 times 10 to the negative 23 joules per Kelvin. That is the value of K. Alright? Now, what we have seen is PV equal to KNT, where I gave you the value of K. You don't need to remember that value. Whenever you need it, I will give it to you. Tell me one more time, what is N equal to? N is the number of molecules. Alright. According to Avogadro's principle, 1 mole of any substance under the same conditions of temperature and pressure contains the same number of molecules. You see, if you take 1 mole of hydrogen, 1 mole of nitrogen, 1 mole of air, all those will contain the same number of molecules. And that number is called Avogadro number, and we write it like this, N sub A. Now tell me, what is Avogadro number? Avogadro number is the number of molecules in 1 mole of a substance. Now no matter what substance it is, that number is a constant. 1 mole of any substance has the same number of molecules. It's called Na. Therefore, this total number of molecules N can be written as, let me give you the value of Na. The Avogadro number is 6.03 times 10 to the 23. There are so many molecules in 1 mole of any substance. Now, since a mole of any substance contains Na number of molecules, if you take N mole of a substance, suppose this substance, this N molecules are actually contained in N moles, that means the total number of molecules equal to the number of moles of the substance multiplied by the number of molecules per mole, the Avogadro number. Therefore, we can now write PV equal to NKNAT, where Na is the Avogadro number, K is the Boltzmann constant, and N is the number of moles of gas in your sample of study. And now, this green lettering I have, K times Na, we're going to now represent that as a very big constant. And you're going to write it like this. K times Na equal to R, and that R is called the universal gas constant. Now don't forget that. R, the universal gas constant, is K times Na, And look at the way that therefore we can write the universal gas equation. PV equal to nRT, where N is the number of moles of the gas, R is the universal gas constant, which is Boltzmann constant multiplied by the Avogadro number. Now this is the statement of Boltzmann, the ideal gas law. And the value of R is calculated as 8.314 joules per mole per Kelvin. Now write down that value and learn it. The value of the universal gas constant is 8.314 joules per mole per Kelvin. Now we can also have another value for R if when pressure is measured in atmosphere and volume is measured in liters, the value of R will be 0.08206 liter atmosphere per mole per Kelvin. Now remember, both these values are the same, but here the pressure is measured in pascals, volume is measured in meter cube, so that is 8.314 joules per mole per Kelvin. When pressure is measured in atmosphere and volume is measured in liters, the value of R is this. We will now use the concepts we developed so far to solve some problems, and that will be done in the second part of this lesson. I will have a second part that I will take a little later. Alright? So I will see you for that a little later.